All right. Well, welcome to our last seminar, actually, of the year. Thank you all for coming. It's a pleasure to have here today Dr. Baryshnikov from Bell Laboratories, Alcatel-Lucent now. I guess you have to tack that on. From Murray Hill, New Jersey. And of course, Dr. Baryshnikov is very well known in topological modeling, and also as applied also to networks. He's been doing a lot of very interesting research, and today he'll be talking about target enumeration via Euler characteristic integrals. Dr. Baryshnikov got his PhD in applied mathematics from the Institute for Control Sciences in Moscow, in Russia, in 1987. He was a researcher in Moscow, Germany, and in the Netherlands, and he was a professor of mathematics at Dauphine in France.
No, it's not Dauphine.
Not Dauphine. Somewhere in France. Okay. And he joined the Bell Labs at Murray Hill in 2001, where he's currently head of the Department of Industrial Mathematics and Operations Research. Dr. Baryshnikov research interests lie in probability theory, dynamical systems, and global analysis, and their applications to telecom, economics, sensor networks, and self-assembly. It's a pleasure to have you here. Thank you for coming.
Thanks a lot. Thank you for an invitation. It's really a pleasure to be here. Okay, so this work is started and developed over the last couple of years, joined with Professor Greist from Urbana. And I should have mentioned the work was funded and is funded by DARPA grant named STOMP, which stands for Sensor Topology and Minimalistic Planning. So it's a division of math sciences, and DARPA is funding it. Okay, so
who's the program manager?
Ben Mann.
Ben Mann?
Yeah. Okay, so kind of we here, and it seems that it will be reality that in quite near future our environment will become more and more saturated with sensors. So kind of ubiquitous, omnipresent sensors, which will be our sort of extend our nervous system to the environment, to forests, to bridges, to everything which we don't see, don't feel. So and it's not there, but we kind of can foresee it. The device is getting smaller and smaller, and the energy consumption of this device is getting less and less. At some point we'll just we'll be there. Kind of you will not be asking yourself whether you turn your oven off at home. You will know it because there will be sensors sitting there and telling you that. You will be not asking how many deers in this particular grove. You will know that because there will be sensors spread out by EPA and just monitoring them that everything is fine. So we will get much more insight in our environment. So that's but if you think about it a second, you will see that the huge problems will arise when you just try to understand what to do with all this data. It's in some point it will be easier to maintain, to keep the measurements, feed them into the system. What you do with those measurements, how you accumulate them. So to cover some reasonable growth, you need 10,000 sensors there. Do you want all these 10,000 sensors pinging you, all the time, saying, "Oh no, nothing new, or just heard something"? No, you want the aggregation information. The information should be processed somewhere, much closer to the edge of the network. So, kind of the requirement for algorithms which are decentralized, address some sort of questions which seem trivial, but become very non-trivial when you have, a lot of dumb nodes which really omnipresent but cannot think for themselves. You have to aggregate the information. This flood of measurements coming from there. Okay, so kind of one of the basic questions you address when you want to do something, know about something, is to count, right? So how many people is in this room? We can answer this quite quickly. How many deer are in these groves next to this building? We have no idea, right? So counting is one of the basic activities, and let's think about it. Kind of this main task of this talk is, we'll try to discuss, we'll try to produce algorithms of counting the targets or objects. So it will be the primary task we'll address here. So in applications, of course, I'm sorry. It's too sensitive, it seems. Right. So in agriculture, in biodefense, you should be aware of border security, people in vehicles, how many people crossed, are they friends or enemies, how many enemies crossed, how many friends did. In commerce, enormous area of applications, and as I mentioned, environment to understand what's happening out there. Military definitely is interested how many gunshots were fired in this situation, how many people are in the field. Traffic control. So applications are abound, and to understand how to count with this large array, this dumb sensor sitting out there, is very important. So we begin kind of the theory will describe here. It sort of starts with this sort of the limiting situation, right? With the situation where the cow is spherical. Kind of it typically starts with some situation that's easy to analyze. So we consider a situation when sensors at such high density that you can basically assume they form a continuous substrate. So the medium is each point is a sensor. So you have like substrate, and each point of the substrate is a sensor. It returns you information if you ask about it. Well, then we'll talk a little bit about how to do what to do about discretization. So if the sensors are not forming this continuous substrate, so you have to discretize. So you have to work with real life. So how much of our algorithm survives, how much to what kind of discretization issues we have to address. As I mentioned, the sensors already they are not very good, but they will be even dumber in the future, and they will be much smaller, much more densely placed, but they won't have even those computing capacities they have now. Right? The iMods or the standard sensing nodes we have now, still they carry processor, they carry some sizable memory. They can carry operational system. Something operational system. No, there will be no operational system there. The sensor will be really dumb. It will be kind of waking up, measuring something, sending it, maybe adding two numbers together. That's it. There will be not much of you could require from them. So you will have to think about smart algorithms which leverages on these sensors being dumb, but being many. So you have a lot of redundant replicate information. You have to understand how to aggregate this information without taking this task, all this information to the central node and doing it this centrally. So, yes.
Is it all right to interrupt?
Please.
I'm just wondering if the sensor is required to send something.
Right.
And transmit some data. Those two things, right?
Right.
Then I don't understand why you can't put all the smarts in the world into that sensor because.
Right. I would love to, but
No, I'm saying in my opinion, the size of the sensor part and the communications part of the sensor is the expensive part, and the communication part of it by Moore's law is so simple. In other words, it's so you can put all the computing power on these sensors for free.
I would love to. Unfortunately, you have to feed the battery. The battery life is what restricts all the sensors. The sensors cannot operate by as we want them, and putting each battery there is an extraordinarily expensive proposition. The cost of sensors will be the cost of battery which feeds them.
No, I say that the act of sensing, okay,
right.
the thing that senses,
right,
and the thing that communicates,
right,
are the things that are going to run the battery down. The communications are so low power,
right,
that the communication part is free.
Agreed, but computing part is not free.
Well,
it's extraordinarily expensive. If you think about it, oh yeah, absolutely. Think about it. Sensors kind of, if you let that's the problem. The existing sensors cannot, they're pretty sizable because of these batteries. They operate 2 weeks.
No, right. I
because you have to, you have always, if you keep the architecture as it is, with tiny OS, with some operating system, it's always kind of updating, always churning some wheels inside. You're always, producing an enormous amount of heat, and there is no way you can feed it, and especially there is no way you can spread all this, all these awful batteries down there and kind of keep doing it. No, it's energy.
Okay, so you're saying you're not going to put computing power on these sensors?
No, it's.
Okay.
I mean, well, I have to do something about it, but it should be very minimal. Okay.
Okay.
Let's go to what kind of counting we want to count. So kind of again, remember in this paradigm where kind of first consider continuous limit, where at each point you have a sensor. So you have this some planar domain, and each point x and r on the plane on the plane you have sensors. At each point you can count what you can count. So you can count the targets. So you have some finite number of points, some targets sitting around, and something like that. So these red disks are targets, are objects you want to count. So altogether we have 7 objects here, right? And each sensors, so each disk shows where this object is being sensed. So it's very simple model. It's very simple model which shows, that each object is being sensed at given distance r. So there is a sensing distance. At each distance r, you can sense this object. So all points within this disk will sense this object, right? The points in this lens will sense 2 objects, this and that, right? And let's assume that it's all what they can return to you. So they sense if you ask the point x and it says, okay, I hear 2. This means I hear 2 objects. I don't know its object A or B. I just have no idea about their positions. The only thing I can measure is they're there, right? I heard some, some steps. So from one direction, and some steps, and I had another set of steps. There's 2 targets there, so something is going on there. So the people of course returning 4. They will be having 4 targets in the vicinity and so on. So we'll have this picture. So this is red background shows where anything will be sensed at all. So the question is, how we understand how many sensors are there, right? So you get this information. And of course you can say, okay, if you get this information, you can just say, okay, you can just redraw this picture, right? So you have all the sensors, you know where each sensor sits. You can just draw this picture, and then from this picture immediately you see, okay, you know what? Obviously, there are seven guys out there, and the positions of these guys are there. Well, how do you know where the sensors are? Sensors are dumb. You have no idea where they are. So you throw the sensors, and they return the data. You have no idea. You threw them, they were kind of $1 a piece, and you just forgot where you placed them. The localization problem is a difficult problem. To solve it, again, you have to spend a lot of your energy budget. Do you want it? No. So you have these sensors. They return your data. Maybe kind of your sensors know who are neighbors, who are their neighbors, so you can ask them, to sort of interact a little bit with their neighbors, but that's it, you cannot kind of completely localize them, you cannot completely understand who is where. So how you can solve this problem about finding the number of, aggregating the total count into one number, the number of targets? It's very simple, you just integrate. Just because area of each disk is pi r squared, right? And the count at each point is, consider just the function which is 1 within this disk and 0 otherwise. And you sum up all these functions, right? So you get 2 just because this 2 will be the sum of 2 indicator functions, right? So when you integrate this function, so integral for sum of functions is sum of integrals because...
is it okay if you can button your shirt a little more with the mic on the outside?
Oh, I see. It's mic on the inside?
No, not on the inside, the outside. Yeah, it keeps changing.
Okay. The integral for sum of functions is sum of integrals, so you're integrating this function. What you're getting is the sum of integrals of one function, and the integral of one function is pi r squared, right? So if you just do the total math, you get that the total number of targets is just the integral of this function h, of this count function, divided by the area of one footprint. So let's introduce some notation. So this function h, which at point x returns how many targets you are hearing or you are seeing, we call it count or height height function. So it's integer-weighted function which just says how many targets are around you. And the area where this target is being seen is, let's call it footprint. Right? So we have this footprint. So we take the function, which is count function, and divide it by the area of the footprints, because all footprints are the same, have the same area. So we divide by it, and we get the number of targets. Very easy, very nice, natural answer. Okay, maybe it's the way to go. Well, the problem is that quite often this target supports, these footprints, have very different shapes. So let's consider the situation. We have this is target, and this is its shape. This is where this target is being seen, right? This is another target, and it's seen being, it's seen in this sector, but not here. So it's just a fraction of this disk, right? And if you take into account propagation laws, phasing, attenuation, whatnot, you will see that things can get complicated pretty fast. So what shall we do about it? So what if you have to count, situation when, some of the targets are loud, it being SUVs, and some of them being Priuses, very, very, very quiet. So how you can count this situation when the footprints are different sizes, different shapes? Okay, this is our goal to address, is to try to find the answer of what happens if you want to count the number of targets, which each target can have a footprint of different shape, different size. The only thing we require is this footprint has relatively simple topology. By topology, I mean the how complicated is the shape, how complicated is the the basic geometric feature of your footprint. So we will assume for most of our conversation that the footprints will be contractible sets, meaning maybe convex set or star-shaped set for which there is point which sends signals and has the. So it's contractible if it can be pulled by itself into a point. So for example, an annulus is not contractible. You cannot pull an annulus. You cannot draw an annulus and you sort of pull it into itself into a point, because you'll have to sort of break it somewhere. On the other hand, a disk is contractible. Just take a point in the disk and just homothetically pull it to this point, right? So, for example, the contiguous 48 states in America, if you discard the lakes, is contractible set. If you throw in Hawaii, it's not contractible, because you have these two components, with Alaska, right, or Hawaii, or whatnot, right? There's many countries which have enclaves, like South Africa has two countries which are sitting within it, so sort of it's a disk with two holes. Definitely it's not contractible, right? So there's a lot of situations when stuff is contractible, situation when it's not. We will consider the relatively realistic problem where kind of our footprints are contractible. You can think about it as being sort of visual or radio or heat signal being hitting obstacles, but still you're going in some direction, you're propagating. You can always go back towards your target where you started, right? So there is kind of assumption of contractibility.
But on the other hand, like the schematic you showed in terms of, for instance, where your area can be quite complicated,
right?
And I assume those black things are like blockers, right?
Right, it's walls, right, it's walls.
Yeah, those are holes though, right?
No, this is the substrate, if you look at the substrate, it's, this is
what about the black thing?
They're not part of your terrain, they're not part of your terrain,
yeah.
Right? So you not count them as holes. There are no sensors here, So the footprint of each guy is contractible. That's the only thing we have to know.
The footprint of each guy, a given sensor.
Right. It's a footprint of given, not sensors. Okay. Sensors are sitting at each point.
Okay, not the whole area.
The footprint of each guy, of each target is contractible. Right. Like here, right? Take this guy, its footprint is given by this area, it's contractible.
Yes.
Take this guy, its footprint is given by this area, and although it's not convex, but it's definitely contractible.
Okay.
Okay, so how we do it? We use the kind of relatively unusual but very nice and simple notion of integral with respect to Euler characteristic. So let me just deviate and talk a little bit about Euler characteristic, what it is. So Euler characteristic is a way to attach a number, an integer number, might be positive, negative, or 0, but it's integer, to some topological space. Topological space is just this, some set about which you know which points are sort of close to each other. So you can know which points are neighboring in some sense, but that's all of what you care. You don't care about actual distances. You know you're close somewhere, but you're not caring with actual distances. So in some sense you can deform. Topology deals, as you probably heard a million times, topology deals with what remains invariant if you sort of change the shape without breaking or without attaching something, right? So like with kind of standard examples that the coffee cup, coffee mug has the same topology as the bagel which is served with it, right? Because you can deform it. If it were made of mud, you can deform it into a bagel, into solid torus without breaking anything. Okay, so once you have these topological spaces, and this you think about this huge amount of freedom you can apply to these topological spaces without changing anything about them, right? So you want to understand what are the invariants, what are the things which you can measure about these topological spaces, but which survive after you do this transformation, do this rubber changes. Imagine that all things are made of rubber, so you cannot say, okay, the size of the thing is such and such. No, you can expand it. It will be bigger or smaller. But what data you can, what data will survive if you under those deformations? What are discrete invariants? We call them invariants because they don't change when you change the shape of those objects. So the Euler characteristic is one of these objects, and there are a couple of definitions. They work in different situations, and so kind of the easiest way to describe it is the following. So if you have some complicated shape, let's split it into simple parts. Let's split the shape into simple parts. And the simple parts should be, some pieces of various dimensions, some kind of cubes or triangles of different dimensions. For example, you can split, let me just draw an example. Like a disk is already a disk. You don't have to split it. So this is just two-dimensional disk, right? You don't have to split it. It's sort of elementary object. On the other hand, if you have an annulus, it's not very elementary, so let's try to split it. Let's try to split the annulus. So how we can do it? We can put point here, put point there, and cut in the middle. So what we'll get? What we will get? We'll get one two-dimensional disk, right? This is two-dimensional disk because we cut it there, right? We will get 1, 2, and 3 one-dimensional guys, right? And we'll get 2 zero-dimensional guys, right? So let's keep the balance. So 2 dimensionals 1, 1 dimensional 3, and 0 dimensionals 2. In this situation, you have 2 dimensionals 1, 1 dimensional 0, and 0 dimensionals 0, right? So what is Euler characteristic? Euler characteristic is just the alternating sum of these numbers. So you start with 0, it's sign plus. Next one will be sign minus. Next one will be sign plus. So you'll get plus, minus, plus. Altogether, you'll get 0. So the Euler characteristic of the annulus is 0. What we get here? Plus, minus, minus, plus. The Euler characteristic of the disk is 1. It's natural, by the way. We know that sort of it's contractible. So we can contract it to a point, and the point is sort of the basic thing. If you want to have a point, nothing should change if you contract stuff to a point. For the this contractible set, you contract to the point. From our topological perspective, nothing should change. And the Euler characteristic of a point should be 1 because you have just one object of dimension 0. So it's nice. This thing already shows that we cannot contract it, right? If you believe me that this Euler characteristic is topological invariant, it doesn't change when I deform everything, then you should, you can see immediately that it shows already this cannot be contracted, annulus can be contracted to a point. Because if you contract it to a point, your Euler characteristic should be 1. If you cannot contract Euler characteristic, it should be 0. So what we have to check, is a definition, but of course you can say, okay, you know what, if I add a couple of points there, I get completely different numbers. Right? That's true. So how the numbers will change? We'll get two two-dimensional guys, right? You'll get 1, 2, 3, 4, 5, 6 one-dimensional guys, and we get 1, 2, 3, 4 zero-dimensional guys. The number is still 0. So this is the topological invariance. This shows that the Euler characteristic doesn't mess up things. Okay, so Euler characteristic is invariant is the number you can attach to any topological space. And how we use it? First we learn the properties of Euler characteristic. So in some senses, this is kind of some generalization of the notion of cardinality. So if you just set a bunch of points, discrete points, not connected to each other, the Euler characteristic of this bunch of points is just the number of these points. Right? So if you want to count with respect to Euler characteristic, if what you're counting is actually just points, then you are in the luck, because you just take the Euler characteristic, it will count it for you. Right? Okay, so as I mentioned, if if it's deformed, can be deformed to a single point, and just by invariance, by the homotopy invariance of Euler characteristic, you will get again 1. If you have a graph, so if you have a graph consists of points and edges, then obviously you have number of points, which is 0-dimensionals, right? Minus the number of edges, which is 1-dimensional guys. For the triangulated oriented surface, which I know people do a lot here, so the of genus G, so if you have like sphere with G handles attached to it, like a bagel is just one handle attached. We can think about German pretzel, which has two handles attached, and so on and so forth. So the Euler characteristic will be 1 minus 2 times minus 2G, so 2 minus number of handles you attach. So for the torus, when you attach just one handle, the Euler characteristic will be 0 again. And very important fact is that if you have something on the plane, which is connected set on the plane, what's connected set on the plane? Just some disk from which you removed some holes, right? So the Euler characteristic of a disk from which you removed n holes will be 1 minus n. So like in this example, this is disk where you removed 0 holes, so Euler characteristic is 1. This is the disk where you removed 1 hole, so Euler characteristic is 1 minus 1 is 0. Right? So Euler characteristic of South Africa, which is just the disk with 2 Lesotho and forgot the name of the other country removed, will be Euler characteristic will be minus 1. Okay, so and there are some sort of so far we just were looking at the example, but there are some abstract properties of Euler characteristic which are relatively easy to prove. Let's just formulate them, and one of them is additivity, which says, okay, if you take two sets, maybe overlapping, then the Euler characteristic of their union is the same as the sum of the Euler characteristic minus the Euler characteristic of intersection. It's a very natural, very nice property. Okay? Another is multiplicativity. So you have a direct product of two sets, then the Euler characteristic of this product will be the product of Euler characteristics. Okay, so immediately if you look at this, you remember something. Like it's the definition of the measure, right? So if you have, say, probability measure, kind of your course in probability theory, so if you have two sets, what is the probability of being in two sets, of having union of two events is the probability of one event plus probability of the other event, but you have to subtract something, like the overcount. You're subtracting the overcount is the probability of this event. So in this sense, Euler characteristic behaves exactly like a measure, which you probability measure, which you encountered in probability theory. And what you do in the measure, you have probability measure and you have a function. You can integrate a function with respect to measure. Right? So let's try to do so. So let's, you cannot integrate any function. In probability theory, you have functions which you can integrate, measurable functions, and functions you cannot, non-measurable, right? So you have to restrict the set of functions we plug into the black box, integration black box. So let's consider only the functions which are you take good sets, this U case, and this U case will be these footprints, essentially will be footprints of what we will consider, and take some weighted combination of these footprints, for example, just the sum of them. Then we define the thing, so the integral with respect to Euler characteristic is just the sum of these coefficients. So if the footprints, so if this all U case are contractible, are compact contractible sets, then the integral is just the sum of these coefficients. Let's get another example. So consider just set on the line and consider the function like this, which is 1 on this interval, is 2 on that interval, and 1 again here, and 0 elsewhere. So this function is obviously can be represented as sum of contractible ones sitting on contractible sets. For example, it will be sum of this guy plus that guy, right? So it will be indicator function of set u1 plus indicator function of set u2. Summing them up, you're getting our function. So the integral of this function will be 1 plus 1 will be 2. What is important to notice that it's not kind of, we know the function. From the beginning, we know the function. We don't know how to split it into these particular sets, because the splitting is by no means unique. The same function can be represented as sum of this function plus that function, right? So we know the function, but we don't know the splitting. We don't know how it was composed. So even in one dimension, you have this huge ambiguity, and you have higher dimension, like in a plane, this ambiguity is bound only to increase. So it's not trivial fact that despite all this ambiguity, the integral is well defined. So however you represent a function as a sum of such summands, the result, the output of this black box will be the same. And this output is called the integral with respect to Euler characteristic. So how we compute it actually? So well, the good way is to we have some kind of way of doing just the standard integral. How you do integral probability theory? You do Lebesgue formula. So how Lebesgue integration works? You take slices. You take slices of your function, and to take each layer, take the layer at level 1. So assume your function has only integer values. So you take a layer at level 1, all the values where the function is equal to 1, and you take the measure, the mass of these points, sum them up. Take the layer which is equal to 2, take the measure of these points, multiply by 2, and add. Take the layer which is equal to 3, multiply by 3, and so on. Right? So you can do it here. For example, how we do it integration in this situation. So let's consider this situation. This is our function. So what is at the level 1? What is the so at the level 1, the function is equal to 1 on this half-open interval. So this point belongs to this interval, and this does not. This point belongs to this interval, this doesn't. So what is the Euler characteristic of this guy? Well, we have to, it's not exactly what we considered before, so let's kind of try to split it into some parts. So this guy is just a closed interval minus 1 point, right? So this by additivity, so if you add 1 point, we'll get 1. So if you take this Euler characteristic of this interval, add 1 point, so add 1, and we'll get 1. So Euler characteristic of this guy is 0, right? So Euler characteristic is equal to 0 here, and obviously is equal to 0 there. And this is just closed interval, right? So Euler characteristic is equal to 1 here. So if we do this, take layer, this is at level 2. We'll take 2, multiply by this Euler characteristic. We'll get 2 times 1, 2. So this is, we know already this integral is equal to 2. So this is the formula. We can also a little bit play with it, with this formula, like closing the bracket here. Then we can not only sum with these weights, we can just sum all the values which are sitting up. So there are some various ways to sort of reorganize this formula, which are useful in different stages of this project. But kind of, I just want to convince you that you can really actually compute this formula. It's rather fun to do examples. I really advise you to kind of take some function and try to compute it. Okay, so let's go back to our sensing story. So assume you have these sensors, and you have this kind of continuous area, and the sensors cover it densely, continuously, and you kind of have the function which returns you how many targets this particular point X is hearing, right? And you assume that each so each footprint is contractible. So for each object, the set of sensors which can hear this object is a contractible subset, compact contractible subset of the plane. Then the number of targets is given by the integral with respect to Euler characteristic of this function. So you take a function, integrate with respect to Euler characteristic, you get the answer. And the fact that it's they are contractible, or rather that the Euler characteristic of each set is is quite realistic. As I mentioned, we have all these footprints are contractible here, so it's not some wild assumption which is never verified in real life. Okay, so let's consider some examples. So this is you see this real life example. So you have a lot of footprints. So some object which has this footprint, right? some another object which has that footprint. So altogether you have 7 footprints, and if you look at it, you know, if you take a pencil and you play a little bit, you can see that there are 7. But if you just have 20 of those, you have no idea. Kind of, it's really difficult to disentangle it's, you know, the whole web. And of course, even you with your capacity, sort of looking at the picture with your eyeball, which is enormously powerful, and your brain, it's an enormously powerful couple of devices, already have troubles to disentangle it. What to, you know, how these poor dumb sensors in the field, how they can do it? Well, they should do what we told them, you know, to use the integration with respect to Euler characteristic. So let's just split it into these layers, right? So let's take the layer. So we have just to take Euler characteristics with this function. This is the sum of Euler characteristic of the excursion sets, of the sets where the count is greater than k. And you take the Euler characteristic of all these counts and sum them up. You should get the answer. So this is where the set, the count is greater than 4, greater or equal than 4. It's just 2 patches. And each patch is contractible. So Euler characteristic of this guy is 2. So this is the last term. Where the function is greater than or equal than 3, these are these 3 blue patches, right? So the Euler characteristic is 3, is shown there. What we have here, the green stuff. And the green is quite interesting. So we have altogether 4 connected components, right? We have 4 connected components. And 3 of them are just disks, have no holes, but one connecting component has a hole in it, right? So you have, you know, this you know, small pieces will have Euler characteristic 1 each, and this big guy will have Euler characteristic 0 because it's one disk with one hole, right? So and this basically tells you what you actually have to do in this plane situation. In the planar situation, you just in each layer you take the number of components and subtract the number of holes, right? Or equivalently, you can take all the layers, and for each layer, sum the number of components, and for each layer, subtract the number of holes, right? So for example, the last layer, you have one big yellow component with 2 holes, so the Euler characteristic will be -1. Right? So it will be -1, 3, 3, and 2, sum them up, you're getting 7, exactly as we started with. So you started with 7 targets, you're arriving at 7. But now it's sort of completely localized because you're not asked to reconstruct what happens, how, you know, the shapes are pretty complicated, the footprints of the targets are very complicated, but you're not asked about following them. All computation is completely local. It's a completely local, can be written a very local protocol to find the number of components of something, right? Because the sensors just flood, you know, I'm saying, okay, I'm measuring 3. Who is measuring 3 else? You know, you start, you have the lowest kind of number, you start flooding this information, and you flood, and essentially you get a component of all your, you know, connected guys who have the same layer as you, right? Somebody else in a different component will also flood it and, you know, get a different component. So kind of identifying the number of components is very easy, right? So each component gets this sort of the smallest number of all nodes sitting there, and the smallest guy sends that information up there. So the center gets just very minimal information. This minimal information, based on completely local interaction within nodes, can return you what you otherwise would require complete geographic composition of where what was measured. Right? So it's completely decentralized, very natural, very simple to program mechanism. We'll see. We'll go to programming in a second. Okay, so. But it's not just the situation when you have these footprints, static footprints, and, you know, something happens. You can introduce sort of also time. So can these shock waves. As I mentioned, you have these gunshots, right? They propagate at some velocity. So you have here something at some point, here something else at different points. Sometimes the 2 gunshots can be heard simultaneously. Can you do it? Yes, we can. Another situation, you have your targets actually moving. So this SUV is moving around. So in different points, you have some, you know, you heard one, and then you heard another one, but it's actually the same SUV, right? Can you handle this situation? Let's just talk for a second, just for the sake of time, we'll talk only about the moving targets. So the moving targets is, we have a theorem which essentially says that, you know, the function, the count which you obtain by, you know, sort of integrating the traces of, you know, these moving targets, as long as each moving target is contractible. So like in this set, this time-space picture of each target is contractible, so it's just a disk. It just sits, you know, in this high-dimensional space. But when you project it down, and you just look what happens for a particular sensor, you will see, so this was one guy. So if you look at the space-time, it will be contractible. It will be disk. It will be just have topology deep. And then you project it down, you will see quite complicated curve, which is not contractible because it has a hole. Can we look at it? Yes. Do the same. Our theory says that you just do exactly the integration with respect to Euler characteristic. You will get the answer absolutely the same. So you will see this in the end. You will have this one red component at level 4, and so we will sum up everything. The last one is, minus 31 is this big connected component with a lot of holes in it, right? So there's a lot of your Euler characteristic gets very negative. Total gives you the same number 7. So the same algorithm works in this situation as well. A little bit surprisingly, because again you have this overlapping targets, but still it works. And even by eyeball, kind of to disentangle this network even for 7 vehicles is already non-trivial. If you kind of look at 20 vehicles, it's getting tough. Okay, so for fields to networks. So what happens if you want to discretize? Of course, you have not completely saturated substrates. You have just points sitting, densely, but not completely at each point. So you want to, you sample, right? You throw points densely, but discretely. So you know which points are neighboring to each other. Kind of let them talk a little bit, inexpensively. What happens here? And you sample them and try to reconstruct the same Euler integral. Just as an analogy is your computer doesn't do the Riemann kind of the integration, numerical integration, just by some kind of somehow understanding this continuous picture. Your computer samples this, kind of does the Riemann integral, takes the integral some discrete number of points and sum them up with some particular weights and gets the result. So you have a mesh, but if you throw sensors at random, you don't place them particularly at some particular locations. Throw them at random, so you get some random geometric graph, some proximity graph, which says which sensors are talking to each other, which sensors are close to each other, something like that, right? So this will be your sensor network, right? This will be kind of the edges will denote the proximity of the sensors, right? And of course, the big question is when this approximation is going to work, right? So how accurate it is, when it's, it will be accurate. So we have some theorem which also describes the situation. So if you if your restriction to the network retains the connectivity patterns of all the holes and all the guys, then you're fine. Essentially, the theorem says that if you have some finite size object, then there is some density after which your sampling will be just exact. So kind of from high enough density, you're getting your integral right. There was no systematic error, which you cannot overtake by increasing the density a little bit more. Okay, now I will do the now it doesn't want to change. Okay, now we'll do the applet. So the Rob grad student David Lipsky, he wrote this Java applet, and so this is sensor network. So let me just zoom in so you can see a little bit more details of this sensor network. So let's take some rectangle. It will show you. So you can see this is just magnification. So you see the sensor network, sensors, and these edges, which are unfortunately not rendered too well. They just show the connectivity between those sensor nodes, right? Okay, so you take the sensor and you throw in some intruders. Let's throw in some intruders. Maybe something like some intruder, something like that, and maybe some more and more and more and more. And you run it. And you'll see. So it's always sort of a bit of competition between program and yourself, how better shape you can produce. So it realizes exactly the algorithm I mentioned. Just counting the holes and counting the connected components. And it's a little bit off. So it detected just 8 intruders in lieu of 9. But maybe we should. So there are some situations where it works I decided to rerun it again. This is the power of Java for you. It's excruciatingly slow. Okay, so what is good about it, you can really take some. What's going on here? Something like that. No. What? It always does me for presentations. It works perfectly when nobody looks at it. But for presentations out of 5. Anyway, so kind of this there is demonstration kind of which shows exactly how it works. Let me just try last. Okay, shall we count something like that? We have one intruder. Somehow it didn't count these components. So it was a bug. So let's, but intruder which is intersecting itself pretty often. So let's see how it will detect the guy. Right. So it's overcounted by. I think it was just because of. This guy was right. These 2 guys were registered, right? Okay, so last attempt to. Right. So how many intruders is there? We know it's 1, but it will require quite a bit to really disentangle it if you want to. But I think computer will do it easily. Okay, success. Anyway, so this just shows that we have complete sort of this model indeed works, can be realized in practice, and has significant practical values. Last topic I want to touch is you might ask, okay, what happens if you are not sensing? Again, it's a little bit far ahead, this vision of very dense sensor network situation, but the robotic exploration, or let's say some unmanned devices which can be sent out there and to measure something, right? So you want to count somewhere, but you cannot spread the dense networks, but you can send some vehicle which can walk around the streets of this abandoned city and count how many objects, weird objects they can, how many alien spaceship they can find there. So of course, again, that's the problem of sampling. How precisely you are sampling? How fine is your network? So kind of you can imagine this is the crisscrossing trajectory. So this is what you measured, and you measured 1 here, 2 there, 3 there. So the question is the knowledge precise? Can you be sure that you basically, assume that your targets are there, so you saw all of them, but you need the relative precision not to overcount. So when you can stop from crisscrossing and start running your algorithm to prevent it from overcount. So we have a criterion which says, okay, look, if you have something like that, some area which you didn't explore, such that the function restricted to the boundary of this area has more than 1 maximum and more than 1 minimum. So for example, you start here 1, 2, then you go back to 1, then you get up to 3. So when you go around, you see 2 local maxima, at 3 and at 2. It says that no, your algorithm, you cannot stop here, you have to explore what's going inside. So you have to crisscross it from minimum to minimum, from maximum to maximum. If you have domain where you have just 1 maximum and 1 minimum on the boundary, then you can stop. So if you run, if you do this, do this exploration, robotic exploration, and you have this condition, so that each chamber, each area has the boundary values which are localized. You have just maximum, 1 local maximum, 1 local minimum. then you can stop and you can run your counting algorithm and it will return to you the correct result.
Excuse me.
Yes?
Sorry, I'm a little bit lost. Can you explain what those color bar and the dotted line represent?
Okay, so this is the solid lines are the robotic exploration which already took place, right? So your robot was running around this, many times, right, and was measuring the counts. So the yellows are the points where the count was measured to 1. The greens are the points where the count was measured to 2, and this is points where the count was measured to 3. Right? So we can stop here and say, okay, we can run our algorithm on this network. We can extend the so what we have to do to run our algorithm, we have to extend the value somehow inside, and produce it. So this natural way to extend it just to put all yellow here, put all zeros inside, so put the minimal value, right? And this result will return you correct answer if you don't have situations like that. So a situation when on the boundary you have some two humps. So this is hump. You go from one to 2 and then back to 1, right? And this is another hump. You go to 3 and then back to 1, right? So you have more than one hump on the boundary of each unexplored area. Then you have to explore further. If you don't have such, if you have just one hump, then you can stop. Right? So in this case, this slash line shows where you have to explore, what next path you have to take to improve your integral. So you cross there. If the new integral, for example, if all values returned on this line will be yellow, the counts will be 1, then you can put this yellow line and stop there, right? Or for example, here you go there and all of them are return count 3. You can also stop, kind of not explore further. So it shows when you can stop exploring and then you have to continue exploring.
So these paths actually is the path of the robotics?
Right, it's robots.
Okay.
Robots are some measuring device which kind of measures it. Again, it's not the sensors which are kind of switching gears. It's not the sensors which are sitting there. It's just you explore it. It's robotic exploration. So they kind of just trying to prove that the same algorithms can work in the situation of robotic exploration when you don't cover the whole two-dimensional substrate or high-dimensional substrate, but have some one-dimensional, much smaller set which you can cover. Okay, so I think I'm very close. So this is essentially, it gives you an exploratory strategy, how where to go next, which is important for robotic exploration because you don't want to just randomly wander there. Okay, so what we introduced is, the tool, which is useful tool of integration with respect to characteristics, show that it's, kind of does the work which you want from the sensors to do, to take this local information, abundant local information, integrate it into something global. And this is exactly why kind of the topologies so nicely fit here, because topologies, you have the local information, know which points are close to each other, and to try to extract something global. This is exactly what happens here. So this nice, very nice and relatively rare situation when some kind of global consideration can lead to some very practical algorithm. Okay, thank you.
I have time for a couple questions. Yes.
You started your motivation by arguing that instead of having a larger number of dumb sensors, it's better to have a smaller number of smart.
No. If you have large number of dumb sensors, that's the future. Large number of dumb sensors, right? That's the future, yeah.
Okay.
And probably, yeah.
But there's something that I failed to see, the exact connection between the counting problem and the actual number of sensors. I didn't see how the counting problem falls into having...
Well, kind of the theory essentially was built for the situation when the sensors are so dense, there are so many sensors that are sitting essentially at any point. Mm-hmm. Then we relax it a little bit back and say, okay, if they're not just sitting at any point, but just dense enough, then you can successfully count.
Okay.
Right.
Okay.
So again, the problem is you have very dumb sensors, each of them shouting that I see 3, I see 2, but there is clearly an overcount because they see the same targets, but they have no way of distinguishing between the targets they're seeing. Right. So how to integrate all this avalanche, this flood of information into some one number is all it is about.
Yeah, you're looking at this point just at counting. Are you eventually going to look at being able to identify a target if a deer walks through, as you brought up, a deer walks through the forest and you try to see there's a deer walking through,
right,
you can tell where it's going?
it's a fair question, but it's sort of engineering question, kind of, or rather, like if you have your set of tasks, right?
Right.
And, your set of tasks may evolve and can look into differentiating differentiating targets, understanding something more about them. But I'm kind of again the main story here is that if you restrict your task, and your task is just simple counting, right? You restrict your task to counting, then you have assume extraordinarily little about your sensors. So kind of your sensing ability is extraordinarily weak. You don't know where you are. You don't know what you see, right? You don't know when you heard it, right?
Okay.
Just you have you got this number from somehow, right? You just heard like 3 times you heard the gunshot. You don't know when, right?
Okay.
And you just talk a little bit to your neighbors, and still this is enough for you to reconstruct the whole picture.
Okay.
Right? Without sending all this information to the center,
right,
overwhelming the center, yourself, and whatnot, just doing it. So, right. Of course, different tasks require for different modalities, different algorithms.
Understand.
Simple task, simple algorithm.
Right, I understand.
Any other question? But in a practical setting, though, when you're defining the levels, what are the measurable? From let's say, for instance, in the field, are you measuring the power, or what are you measuring exactly?
Well, kind of the sound, the sound triggers, like counting the vehicles moving around. It's natural. So you once you hear the sound going above some threshold, you click OK something.
Okay.
The sound goes below, you say OK, that was one event.
Okay.
You just count the number of such events. When you hear the sound, jumping up.
How does a sensor know what its footprint is?
No. Sensor has no footprint. The target has a footprint. Target has a footprint, and sensor has no idea what the target footprint is. Just hear it or not. Target has a footprint. Target's footprint is the set of all sensors which hear it. SUV or tank has a footprint as all the sensors which can hear this tank. A gunshot has a footprint, just all the sensors which can register this gunshot. A deer has a footprint, all the sensors which can feel its heat. Right. So the footprint is footprint of a target is the set of all sensors which can register it.
And that, of course, depends on how many sensors there are, right? Or not?
Right, of course, but again, assumption is that the sensors are dense enough, so we saturate them. Assumptions throughout this talk, with the exception of the last one, where there was robotic exploration, was that you have very dense field or very dense network of sensors which register what they hear, what they know. Right. So once again, kind of think about you have the sensors which have cost 50 cents a piece, and you take 1 million of them, right, and spread it on some some field, and then just ask them to tell you how many gunshots they heard, right? And after a day you integrate and say, okay, there was like 15 gunshots in this area, right?
So who do the sensors talk to? Each other, or?
They talk a little bit to each other, yeah.
So the sensors talk to each other?
A little bit to each other, yeah.
And then some sensor tells you what the
you can, right. It's a little bit different story. So networking protocols of communication between the sensors and the center can vary. For example, you localize for example, it's like when you want to localize a connected component. So you want to localize all the sensors, connecting components of all sensors which heard 3 gunshots. How you do it? Kind of, you can kind of create a protocol where the sensor, sort of start thinking about it in some cyclical order or maybe some random order. So the first sensors think about it and say, okay, I'm free, and tells it to his neighbor. His neighbor says, I'm free as well. Who else is free? So they kind of flood it. They create a standard procedure, flooding the network until they exhaust it. So they say, I'm free, but I already told you that, right? So, and they say, okay, so we are all 3. Who has the smallest number, kind of the smallest node number among us? Or some, whatever way of selecting some particular nodes. The node says, okay, I have it. You talk to center. So just one node, and this whole connected component talks to the center, to the sink, and says, okay, I heard three kind of, there's one connected component here which heard three gunshots. Another connected component, there will be one sensor from there and say, okay, so the sensor will say here, okay, this guy say 3 gunshots, this guy say 3 gunshots, and this guy say 3 gunshots. So we have 3 connected components with 3 gunshots. That's enough. If you collect all this information, it turns out to be enough to gather it. Again, kind of this essence is how little you have to know to integrate it, to capture. You have no idea of what kind of geographical position of this sensor, no idea of where these gunshots actually happen, but still you can count them.
The challenge, basically, the idea, as I was describing this morning, is to use these level sets to get a whole integrated picture of the sort of the conceptual idea. Okay. Well, if there are no more questions, let's thanks for the